let's begin. Because we have the recording, so even though there are still some students not coming, we will just begin. Okay, so if you missed the first part, you can watch the video. Right? So, and yeah, last time we talked about some machine learning tasks, right? Supervised learning and unsupervised learning. Who can tell me the difference between supervised learning and unsupervised learning? You can unmute yourself and if you want to answer. Yeah.
So according to me, supervised learning is more about making the predictions, but unsupervised learning is where we don't have the target and we are trying to look for the interesting patterns. Like, for example, grouping the type of customers in a shop, or grouping, identifying the interesting categories or something from the existing data where the target is unknown.
Yeah, exactly. So basically, put simply, if we want to make really things really simple, then we can see some. So we are now using, I'm using this editor because my handwriting may not be clear enough. Okay, so let me keep these because we will be using them later. Okay, so let me have some new lines. And so basically, in machine learning, if we are given X and Y for training, right? So okay, so basically we are all having this function for supervised learning, right? So for example, if you are given X, okay, and you're also given Y, let's say given the image and you're given the annotation, where is the car, for example, right? You're given the bank health record for a person, see whether this guy has a disease or not, right? So this is supervised learning, okay? In supervised learning, you just look at the data itself. You only have X, you don't have Y, okay? And then you will see, hey, these guys can be clustered into two categories, and then you may guess, oh, this may be this disease, this may be the health people, for example, right? So you don't have Y initially to train you, right? So there's no supervision. So this is basically the meaning, okay? So this F is the model, right? So X and Y are the training data, okay? And the prediction is you have X, you don't have Y, okay? So this is for supervised learning. Theta is a weight matrices we want to train, configure the model, right? So this is what we have here. And so let's begin. Go back to where we were. Okay, so right. So unsupervised learning, basically, we don't have any supervision, right? So supervised learning, we have classification and regression, right? These two kind of problems, okay? Unsupervised learning, we don't have Y, so we don't have any such concept, right? So we have, so no output is given. So basically, we are saying no Y is given, okay? We only have X. And it's not so well defined. Let's say if you see three clusters, whether they are really making sense or not, right? You need to scrutinize the results yourself and make sense of it. Right? So, and typical application of unsupervised learning, for example, one is density estimation, right? So we will see where density estimation is used. Let me give you a simple example why we need a density estimation. For example, let's go to Google. Okay. For example, let's take a look at, I believe we have some diagram. Okay. Kernel density. Okay. So for example, you might want to predict, let's say you see a lot of, this may not be easy to interpret. Maybe this is a better way. Okay, so for example, maybe you see like on a road, right? So how many cars are passing by? So in peak hours, maybe you have two modules, right? So this is where people go to work. So that's where people go to home, right? So there will be some traffic here, like people go grocery store, especially there's a lot of housewives, for example, right? So they do not need to go to work, right? So and also some like nightlife, for example, right? So in this case, right? So we will see these two modules, right? So how can we simulate this distribution, right? So if we consider the whole distribution as like a one, right, probability distribution, how likely they are distributed along on this road? How likely the traffic is distributed along the day, right? So, for example, for this case, you will see some sample data, right? Hey, you have these cars coming very dense here; these are very sparse, but you don't have all the data, right? So, if you want to fit a density function for this, right? So then you can use this clustering kind of method, right? So you don't have the ground truth, right? You only have X, which are those what you see, right? And then you want to fit a density here. Okay, so this is density estimation, and this can be used as a module. Let's say, so basically, there's like a Bayesian method, right? So basically, we are saying that if you have a condition, how likely you will generate an outcome. Okay, and this kind of conditional probability kind of modeling can be concatenated into a graphic model. Okay, and so these days, if you look at deep learning, they are kind of using a given up solution, right? So for example, if you have a graphic model, all the factors, input factors, output factors. So I just make it all connected, okay? And I give up my control modeling of this relationship, like in a Bayesian network, okay? I just let all the connection learn their weights, okay? So this is also a kind of graphic model, but it's a given up solution, right? So I just let the data tell me whether this connection should have a high weight or almost zero, okay? Right, so for this kind of module, maybe one of this probability distribution, like conditional probability distribution, is like the traffic, right? So how likely is this traffic, right? And then we are predicting how likely there will be collision, something like here, right? So one of these module might need to be fit from the data, and we can use density estimation, right? And this could be just one module of a more complex model, okay, that we see. All right, so this is one example. You only see X, right? And you guess how it's distributed. Another is, for example, the dense dimensionality reduction, right? So this is mainly for visualization, like PCA, right, and T-SNE, right? So if you have 1,000 dimension of that data, right, it's not easy to visualize, right? So you have maybe a lot of attributes in your health record, right? And but actually they can be, if you map them into low dimensional space, right? You can clearly see they belong to two different clusters, right? So those people maybe are having health problems, obesity, right? These are health, okay? And so in order to do that, you have to reduce to two-dimensional space, for them, right? So there are also three-dimensional space where you can rotate, right? So basically we need a dimensional reduction to do this purpose. In this case, you also just see their health records and you don't see the label, right? So you want to make sense of them, right? And see how many clusters there are, okay? So you only see X, right? So this is supervised learning, right? So clustering is another example, right? So basically they are all relevant, right? So, but density estimation is really guess the probability density function, PDF function, right? And the clustering really just see how many groups there are, right? And then you will see how many, like whether each group makes sense or not, right? So there are also other kind of more complex models, right? So for example, if you look at a model called latent error LDA, okay, latent differential allocation, okay. So what it gives is actually a more complicated than clustering. Okay, so let's take a look at some topics from there. Okay, so yeah, so what it does is actually, if you look at the output, so this is all the vocabulary in your documents, right? So this model basically reads all the documents, okay, and then build the model. Okay, after that, you will have so-called topics. The topics are hyperparameter, which means you need to predefine it. Okay, let's say I expect there will be 100 topics in the document. Right? I put 100 there, and then it let the model, this is the graphic model, okay, read the document, okay. After reading these parameters there will be set, okay, so it's conditional probability, for example, because this is a probability model, okay. After that, it will output those topics as a probability density of the words, right? So let's say if all highly probable words are on one topic, some are on another topic, then I can guess what they are about. But you don't directly get those topic names, okay? For example, so this is another example of supervised learning. Let me see. Yeah, so topic modeling. So here's example, let's say. So what they will do is actually they do not have a clear topics, right? So but you can guess from the words in high probable words, right? So the more probable, the larger the words here. So actually what happens is actually what it gives you is something like right? So something like this, right? So these are the top 10 words, and then you can guess maybe Clinton, Bush campaign, maybe the politics, right? So presidential election, and some are like book live novel, right? Books and more like a book reading, and this is more like a music, right? So but you don't really have the why. Okay, you finally make sense of it, right? So this is more like clustering, and this LDA. LDA is more complex than clustering. It can be looked at by clustering because you have the document, you have the words, right? In the middle, you have the topics. Okay, and we will not go over this, unfortunately, because of the time limit. But it helps you to understand what is unsupervised learning, right? So so examples, for example, if you want to do customer segmentation, right? So you want to see for your product how many markets are there, right? So who you should target, right? So of course, go to the market, you don't know how these customers are liking your product now. So you only get their features, right? Their historical purchase record, right? And then what you learn is, for example, right? So for this product, you want to kind of do clustering, right? So find, oh, these customers may like my product, right? According to those attributes, and then you can do more targeted advertising. Okay, so another example is image compression, right? So for example, if you have an image and you see, for example, let me give sky. Let's take a look. Yeah, so for example, you have an image, something like this, right? So if you want to compress it, potentially, even though this pixel and this pixel may have very different color, right? So it's still slightly different, okay? But they are almost the same. You can all use a blue color to do this. This may be purple, right? So this is maybe red or orange, right? So you kind of say, hey, although there are so many different colors, I will just say they are of the same color, right? So I want to use limited color so that I can use much smaller size to encode it, right? So otherwise you have RGB. Oh, by the way, I see an equestrian. Oh, of course, dimension reduction will lose tons of information. I think there's a student asked. Okay, so but you can make sense of how many groups there are. Okay, this is the purpose, right? So you encode high dimensional information into low dimensional information, right? But you still get a sense of some information. We will cover the dimensionality reduction later. Okay, so yeah. So, yeah, in the last part of this course. Okay. Unfortunately, maybe we will not cover a lot of machine learning stuff because there are so many. Okay, we will cover the mainstream ones and those that are common sense to people who learn machine learning. Okay, the more advanced topics you will have to explore maybe after taking this course. Okay, and again, because there are so many libraries, right? So you actually, even if you don't understand it, you know what it's doing, what's the input, what's the output. You can just call the Python library. Okay. So another example is bioinformatics, right? So bioinformatics, for example, you have the gene data, right? So you want to find similar genes, right? So this is another example. For example, let me give you there's a package called WGCNA, which is actually widely used. Okay, so what it does is actually it look at the gene test, right? So maybe this is a good example. Okay, so you do a lot of tests, right? So in different conditions, right? So these are the genes that are coming from the machine, right? So and you do the test. This is microarray, right? So you do the different conditions and see what happens, how it reacts, whether it's activated or not, right? So there's a value here. And then you want to see those that kind of have the same behavior, right? So then they probably belong to the same function group, right? So they are the same gene, right? So this, in order to do that, what they do is they build a correlation, right? So if this gene and this gene are highly correlated, then like this curve is, the correlation is high, right? So then we think we get a high score. Otherwise, we get a low score. Now, finally, we will get a gene. Oh, this is not test. Okay, this is already after processing the correlation matrix, right? So this is the covariance, right? So how they react. Let's say this probably is more correlated with this, right? Because where you activate, here is off. After that, we can build a correlation matrix here, right? And based on the correlation matrix, we can see how close they are, right? So then we are doing some clustering. Say, hey, these two genes are close to each other, right? So this is called a hierarchical cluster, right? So the closest two are put together first, right? For example, their correlation are closest. We first put them together, and then we see a little bit farther away and farther away. Right? So, but we will not cover this method because this is not an optimization method. Right? So most likely in your data mining course, they will cover it. Okay, so this is called a dendron, by the way. Right. So the purpose of this first chapter is really to get everyone familiar with those concepts and in high level. Okay, not the technical details. So yeah, build a mindset for machine learning. And so next is reinforced learning, right? So we put supervised learning, and finally reinforced learning, right? So this is kind of in the middle ground, right? So because, for example, if you play AlphaGo, right? And AlphaGo can play with itself, right? So try to win itself, right? So this is means that you have actions, okay? So reinforced learning, you have actions, what you do, right? So you have actions after actions, like you play the chess, right? Where you put your, what action to take. Okay, so and then you may lose. Okay, so there are actually two concepts. One is called exploration, and another is exploitation. This is kind of like a evolutionary algorithm, right? If you know what it is, basically it says if you already know something is good, you are exploiting it, right? But if you keep there, but you will not find something new that may be better, right? So you will have some exploration component outside. Okay, take some actions that may not be what you always know it's good for this moment, but maybe that's a right move, right? So gradually you will move to the right direction. Okay, so this is reinforced learning, and it's kind of different from the previous example because previous example is something like this, right? So oh, by the way, we will take attendance today by sampling some students. Okay, let me see where's the, maybe I should do this here. Okay. Previously, our problem is super simple, okay? So there's no sequence, okay? So this is a simple model, right? You have X and you give a Y, right? So, and usually in this course, we will all looking at this kind of problem. Just let me add something, okay? So this may not be, Y may not be a vector, okay? X is always a vector, right? So it's X1, X2, X3, different attributes, okay? And Y usually is one value, right? Classification, it's a label, regression, it's value. But you can have multiple values also, okay, in a lot of cases. Let's say the multitask learning. We see where the cat is, right? What's the X1, Y1, X2, Y2, along with, for example, whether it's a cat or a dog, right? So it's image localization application we talked about, right? So Y can also be a vector, as long as you have a loss function that can be defined on all those target goals, okay? And so we will look at what loss function is in later part of this course. Okay, let's continue. So so there's no supervised output directly, right? So in the previous example, we have only X, right? So X1, X2, it's a vector, right? Now in reinforced learning, it's more like you have X1, and you may have a sequence of actions. Okay. From here, 3, 4, okay, something like this, right? So you have a sequence of actions, and finally you know whether you win or not, right? So if you are playing like Super Mario, right? So and then you go, and then sometimes you want to jump, and sometimes you want to jump in this way, right? So and you get a mushroom or something, right? So and finally you get a flag and you win, okay, something like this, right? And so this is kind of delay the reward. If you win, then that's good, right? If it's not win, then maybe you need to penalize the theta in this more complicated step, right? Each step will probably share the same so-called like a Q learning in an algorithm called Q learning. This is the action table, right? If you do these actions, what's the reward, right? So you need to adjust all these weights here, okay? After one episode of the game. So this is the major difference. Okay, you have a sequence of actions, right? So and sometimes you can play with yourself, right? So it's just like AlphaGo, okay? Because there's no better player than the AlphaGo, right? And you will explore the space, right? Sometimes you do some unexpected move, right? And hopefully you will have better strategy, okay? And so example of this is a credit assignment problem, right? So by the way, we will not cover reinforced learning, but again, if you have interest, you can let me know. So I can recommend you some very good YouTube videos. So, and so example is a gameplay, right? So, you know, reinforced learning, there are a lot of game playing these days, right? Using deep reinforcement learning, okay, DI, right? So, and robot navigation is another example, right? So because you, for example, your robot arm need to take something or play, you know, do a complicated actions, right? So in order to do that, they need to learn, right? So, and each time the robot arm fails to, like, say, take up some product, right, to put on the belt, for example, then he needs to change his strategy actions until he succeeds, right? So he gets some rewards, for example, right? So these are reinforced learning, and gradually it will improve, right? So I see another chat. So yeah, reinforced learning has different algorithms. Okay, they have their own framework. They have some way to make it work, right? So maybe how to make it a trend, right? So it's totally different from traditional, you know, just a 1x, right? So we have a sequence wise. Okay, so there are different algorithms like Q-learning, policy gradients, those things. But if we go too far away, this course will be maybe 3 times longer, which we cannot achieve that. So this is a broader overview of different disciplines of machine learning, okay? And then if you have interest and you get the fundamentals in this course, you can explore yourself, or you can ask me for the videos, right? So, yeah. And yeah, another example is if you do a market campaign, but you want a long-term profits, right? Maybe you make money this time, but your credit is terrible, and then no one come and buy your product later, right? So this is a bad move, right? So if you play an episode and then you fail, then next time you will improve, right? Gradually, if you explore different types of space, you will improve. A key difference, I think, is exploration, right? So you need to build the action of exploration inside the reinforcement. Okay, different actions. So there's an action, there's a reward. Okay, these concepts. Okay, so there's a unique niche of models there. Okay, different from what we will be learning for the basic models. And some challenge issues is because, you know, there could be multiple players, right? They will impact each other. So yeah, how to accommodate this case, right? Another is partial observation, right? So you only see what happens before. You don't know whether this movement will really be good, or, you know, you for example, you Super Mario, this jump is good, right? Next jump, maybe you go to the ditch, right? So, and so in this case, you know, it's not good, right? So you need to see this environment features, and then you do the actions, okay? Yeah, reinforcement learning can do, basically, if you have actions, right? So if you don't have actions, I think you probably will not use it, right? So because you have different actions, right? So a student asked me whether, you know, if you, for example, one simple example is, let's say you do a what's a key difference, right? So for example, if you have let me see, image. So here we are defining our problems. So for example, if you want to do the stock price prediction, right? So you will see something like this, okay? Right, so if you do regression, let's say I see a sequence here, right? Again, we will not see sequence, by the way, right? So sequence model is too complicated for the basic course, right? So, but I will give you a brief overview of some way you can handle sequence shortly, okay? And this is time series. Then you see, hey, I see this historical data, right? What will be the next movement, right? It will rise or fall, right? Or we may want to predict the next 10 minutes, 30 minutes average price. This is a regression problem, okay? Right. And so what is a reinforcement learning problem, right? So it learns the actions. It's a learning strategy, right? So, hey, I think this is pretty low. I buy, okay? And here I sell, right? And after a while, I think, oh, it may be coming up for a long time, right? I should buy again. And then I sell again. And then you see you make money, right? So sometimes you do a wrong action here, you buy, but you sell here, you lose, right? So the rewards, okay? So this strategy model is reinforcement, right? If you just see the time series and you predict whether it will rise or fall in the next maybe tomorrow, that's regression. Okay. And the reinforcement is not that mature, but it's popular these days because of deep learning. There's a deep mind, those kind of, right? So it's a learning strategy. Okay, actions, how to move, right? AlphaGo, how to play the chess. Okay, and it's basically a sequence of things, right? And another thing is maybe we didn't cover here, but these days it's super popular, is called deep learning, right? So for example, there are models like CNN, okay, convolution neural net, right? So convnet, okay. So what it does is this, right? So there's something called the convolution layer, which is very good. There's also some max pooling, okay? Very good at pooling the image features. If your input is image, you just call this kind of network, right? This module. People find it's working well. This kind of model seems to work well on images, and then you extract the features. And by this way, now this goes to our regular model, right? So this is X1, this is X2, this is X3, okay? And then you can do regression, like this is probability regression, right? And you can do classification, okay? Right, so this becomes this is where we learn, okay? Right, and we also have the loss function. Okay, what that's before is deep learning's task, right? Extract those semantic features in the high level, right? Because we don't know how to extract, right? We have to rely on those models. So this is for image, right? So maybe for sequence, you have, like, say, recurrent neural network, right? So, or, you know, there's STM, GRU, they come out, right? So this is if you have a sequence, let's say the stock price, right? So you have a stock price, each time you have X1, X2, this price comes, right? And by the way, this does not have to be a stock price. It could be a vector, right? So itself is a vector, right? So like our X, okay? So this is more like what we talked about here, right? So like here, okay? We have those X1, X2, X3, X4, right? Each is a vector, right? So in our case, we only consider one vector in the basic course, okay? But if you do have a sequence of vectors, right? So what you do is, you know, in our case, if it's price, it's just a one price, right? So if you have technical indicators of the last 5 days, 10 days, etc., right? So then it's a vector, okay? And this is for each time step, right? Maybe 5 minutes or half an hour or a day, right? So then you predict the next day's price, next 5 minutes price, okay? So this becomes, you know, feature extraction for sequence model, right? So because you don't know, right? So you just see the raw features, right? Price, and sometimes you have like a word embedding. This is words, right? So there's a way to embed the document, read the documents, just like we see before, like the topic model, right? After reading it, it will tell you each word you should encode into a vector space, right? And these words, when you see a sentence, each word in the sentence will become a vector, and then you use this kind of model.
Hey, question. Would this be reinforcement learning if the algorithm was checking the stock price every day and like comparing its performance?
No, reinforcement learning has its own way. So, you know, reinforcement learning, one example is Q learning. So you need to have actions. Okay, so for example, here you have an action. So reinforcement really building this case. So if you have it in the state, in the environment, you see these cases, right? So let's say there's a mushroom, you should jump, right? So what do you do? And what's the reward you get? Okay, something like this.
So it has to be interacting with this environment.
Yeah. So environment is the state is X1, X2, X3. Okay, but you have something different. You have an action space, right? So you know, if you look at what we have here, this X vector itself is the red part. Okay, we also have the green part, and then we have a way to mingle them. Okay, so it's different, and we will not cover that, right? So if you have interest, you can explore a little bit. It's okay.
Sounds good. Thank you.
You're welcome. Yeah. And yeah, it's deeper. So it's not for introductory course. Okay, so let's continue. Again, so what I want to say is really, so deep learning is just a raw feature extractor. Okay, if you look at let me so basically, if image just use convolution net and their relevant modules. Okay, and if some data is graph data, right? So graph convolution network, right? So if you go to image, so what you have is maybe your data is graph, right? So then instead of image, you do extract graphs, and what it does is, because, you know, graph means you have some data, right? So nearby data is closely related, like genes, right? So like the regions in the neural in your brain, right? So or in stocks that are in the same sector, right? So that both are IT industry, they are correlated, right? So then you can use some smoothing nearby, right, to extract a higher level feature. Okay, so it's the same thing, but maybe you will ask where the X vector, right? So the X vector is actually, let me see what it is. Okay, yeah. So each node has an X vector. Okay, if a node doesn't have the X vectors here that extract higher level semantic values, right? Finally, you can give each node a label. If it doesn't have, it's called embedding. Okay, so graph embedding. If you have a feature vector like environment state associated with it, right? So each node, then it's called the graph neural net. Okay, and so you can see really it's just extracting features after the feature. Okay, so what we are here. Okay, after this layer. Okay, we have X1, X2. What model you can use? In case of deep learning, it's always some neural network structures because we need to do so-called backpropagation that we will see later. Okay, but in our case, we can use SVM, decision tree, etc. We can use a lot of things. Okay, so feature extraction using raw features, whether it's sentence, NLP, image, or signal, right, speech recognition, or medical imaging, etc. Right. Finally, convert to this feature. And now what we are teaching here is when you have those X1, X2, X3 vector, how to predict them. So why? Okay. So this is where we are here. Okay, just keep in mind. This is the same for natural language. Right? So the sequence output finally is the embedding of the sentence of the word. It finally steals this feature. Right? Then you can say, hey, this word is whether it's pro the Democratic Party or the Republic Party. Right? So you can see that's a tweet. Right? So this. You cannot directly read a tweet to extract features, but finally using those kind of modules, we can extract some meaningful semantic features. And then comes in what we will be teaching you. Okay. Let me see. There's another question. Yeah. So unfortunately, we will not cover those details, but graph CN, GN, and GN is very simple, right? If your intermediate value data is graph, right? So your input data is graph. Use graph CN. Graph convolution, right? If your input is image, use convolution, okay, and traditional convolution net, okay. If your input is like a natural language or time series using recurrent neural net, right? These days there's a transformer, okay. All the purpose is just to get to the high level semantic features, and we are teaching the last level model. Once you have these X1, X2, X3, right, just like the regular bank data, right? So the age, salary, savings, right, and whether the credit is high or not, right? So regression, right? We are at the last level, okay? Because we had to cover the basic stuff, right? So these other stuff we will leave to other courses, okay? Any further questions before I move on? So yeah, because I didn't cover deep learning, right? So supervised and supervised reinforced learning and deep learning, right? Deep learning is just a feature extractor from raw features that you don't really know how to extract features, right? It's not your age, it's pixels, for example, right? All right, so now next is really, let's take a look at an example of the machine learning concepts here, right? So firstly, we will do a very simple application, which is a regression problem, right? So input is X, target value is T, okay? So we have a ground truth, right? So we generate, so here's what we are doing, okay? We are create a toy data where we use this sign function to generate, right? X and T, okay? And if this is perfect, right? So like every point should be on this green point, okay? But in reality, this will never happen. There will always be some noise, whether it's the mattering error or some other issues, right? Some inconsiderate factors, okay? There will always be some noise that shift your data a little bit from this green curve, okay? So we are also modeling this noise, right? So put simply, input is X, output is T, right? So if you go back to our example here, so basically we are giving you the machine learning thinking, okay? Because a lot of people just think machine learning fancy, but they don't really know how to think about it, right? So if you don't see the right way of thinking it, you can only call the scikit-learn library, right? And so here we have this T, okay? So this is no longer a vector, by the way, okay? and x is also just one value, right? So this is what we have, t equal to f theta x, right? So this is a more generic case, okay? And this is more our case, okay? We have this simple case, right? And in this case, we have a function f, which is sign, okay? But this is the ground truth, by the way, okay, and with some noise. But now we want to, if we have these, blue dots, right? Then we want to learn a mapping from x to t, right? So to predict t for a new x, let's say now if we see another x here, right? What should be the t here, right? So we want to learn such a model, right? And we don't know its sign, right? So what we can do is, for example, we can use a polynomial function to learn it, okay? Something like this, right? So, the ax plus b is one line, right? So if you have maybe I should not use this. Okay, so let's do this. So for example, you may have y equal to ax plus b, right? So this is this is a line, right? So this is like a is w1, b is w0, right? So you may have something like this: ax squared plus bx plus c, right? So this is a parabola, right? So this is this shape parabola, okay? This kind of shape, x y, okay? So this is quadratic, right? So if you have cubic, it will be a little bit more complicated. Right, so you will have another band downwards, right? So how many, like this is order 1, this is order 2, order 3 may be something shaped like this, order 4 maybe go up again, okay? So because this is related to how many roots you have when you set to 0, right? You have 4 roots if it's order is 4, okay? Right, when you solve the equation. Okay, so let me recur it, okay? So then we can come back. Now, here's our question. So I see another question on the chat. So I see people ask whether polynomial curve fitting is variant of regression. Yeah, this is exactly a regression problem, right? So as I said, so we are considering x, but x is just a one value, right? We only have one attribute, right? Y is t, okay? Right. So this is a regression problem because y is a value, right? If it's a label, then it's classification, right? So this is a regression, okay? And if you look at our slides, we are talking about it's a regression. Okay, a simple regression problem to illustrate our idea. Right? So even though this is a it's a simplest case where x and y are both scalars, right? It's not vectors, right? Even for this case, right? So our parameter theta, right? So if theta is right, theta is actually a vector, okay? Because we can have w0, w1, w2, w1. Any questions?
I have a question, Professor.
Yeah.
Here you are assuming only one input variable, right? What if we have multiple input variables? What could be the polynomial function then?
Yeah, let me answer this question. Okay. So this is x1, it's okay. This is t1, or we say y1. Okay, this is one input data, and you may see 10 input data as 1,000 input data. This is y2. It's okay.
Actually, I'm asking multiple inputs. I mean, multiple input variables. I'm asking.
Oh, you are talking about this is vector, right?
Yeah.
Yeah, if this is vector, then you have another dimension. This may be x1, this is x2. It's okay?
Okay.
And this is your y. Yeah, so it's high dimensional,
Okay.
right? We are using simple case, okay, to illustrate, right? X can be a vector if you have another function, okay? We are just illustrating some concepts like overfitting, underfitting. So we want to use a simple example to illustrate some important concepts in machine learning. That's why we are using the simplest case. It's okay?
Thank you, Professor.
You're welcome.
Professor,
yeah.
Yeah, so in the previous graphs, I can see that the function is perfectly fitting to the data. I mean, though it's not so perfect, but it's almost perfectly fitting to the data.
Yeah.
So which one is more efficient, the linear or the polynomial? So I mean, for the
yeah, we will cover that later. Okay, so this question is actually invalid in some way. So you will see why later. It's okay? Yeah. let's go through a few slides and it probably will be clear. If by that time you are not clear, you can let me know.
Yeah.
Okay, let's say during the break. Okay. All right, let's continue then. Yeah, so as I said, so you see there is x1, y1, right? x1, y1. Okay, you can see x2, y2. Okay, so here, actually, when your training data is given, your x and y are fixed value observations, okay? And for a particular x, let's say 2, you also know this is 2, this square is, 4, right? And cubic is 8, etc. Okay, so the unknown variable actually here is the w's, okay, the w vector is what you're actually training for the model, okay? Because x, y are what you see here, okay, in the previous example. If you go back, right? So this is x1, this is y1. For this point, this is x2, this is y2. For this point, it is x3, this is y3. So these x, y for training purpose, they are actually constant, okay? And the parameter is what you train, right? So it is the target to optimize, right? So you want to find such a w vector to put in this function, such that when you give those x1, the value is very close to y1 in here, okay? X1, so the value is very close to y1. And if you give to x2, the value is very close to y2, you see here, right? X2, the value is very close to y2, okay? So this is the purpose. So if you remember what we talked about for scikit-learn, you have the fit, right? Fit, you give x and y, you fit those w's, parameters for the model, okay? And then after that, these parameters become fixed because the model is built, right? Then your task is you give it x, then x becomes unknown, and your prediction is y. Okay, so then the task case, then w is fixed. Okay, the training case is really training to w. Another thing I think is the student just asked about m. What is m? M is nothing for you to train. Okay, it's an assumption, right? So, for example, if you assume this can be approximated by a line, this is obviously unreasonable, right? Okay, so you can make a line fitting here, right? So, but there will be a lot of error, right? So this is not a good fit, right? So maybe the function is too simple, right? So, but you don't know which M you should get, right? So one way is you try different M's, okay, and see which fits the best. Right? So this m is the order of the polynomial that you had to give to the function initially, right? So we call this parameter w. Okay, so it's m. We can call it a hyperparameter. Okay, this is not a part of where we optimize. You should define it. Then your no, I think this word is wrong. Okay, it's hyperparameter. Okay, this should be one word. I just added space in between to make it clear. Okay. So hyperparameter is what you give to the model, and then the model has those parameters defined over it, right? Because hyperparameter defines how many parameters you have, okay? Okay. And then you see those x, and you want to close the gap between the actual y and predicted y, right? So you see, and then you want to find the w that minimizes error, okay? So there's a loss function defined over the predicted y and your true t you see, okay? So here's the problem setting. Any questions before we move on? All right, so as we said, there's no correct models. There's only models that are useful, right? So for example, here we are using polynomial, but obviously this is a sign, right? If you want to really build a true model, you're using the wrong function, okay? But let's see, this actually works, okay? So so another question is whether this is a linear model or non-linear model. Who can answer me? Do you think this is a linear model or non-linear model?
Non-linear.
Why?
Because we have powers for the axis.
Okay, so this is the wrong answer, right? So this is a linear model, okay? Just one moment. Unfortunately, I cannot find my mouse. I will get my control, okay? Because I cannot use slides. Yeah, let me clear it. I have to use a slides pane. Otherwise, I think Zoom has a bug here, okay? No. Yeah, so this is a linear model, okay? The reason very simple. Our parameter to optimize are w, not x, okay? For example, if you have a point, let me go back. Let's say, just one. Let me take my mouse back. Yeah. So for example, here you have 2, right? And then this may be negative 0.5. Okay. Right. Something. Oh, this is not 2 actually. I assume it's 2. Okay. Maybe 0.8. Okay. Then if you go back to here, this is what? This is 0.8. Okay. This is 0.8. It's a constant. This is 0.8 square. Okay. This is 0.8 to the power of n. They are all constant. Okay. Right. The variables are here. Is this okay? Sami, are you okay with this?
Yes, it makes sense.
Yeah,
yes.
so this is the linear function, okay? So because when you train, you are training W. X are constant, okay? No matter how many powers, they are still constant, right? If this is 2, this is 4, this is maybe 8, 16, it doesn't matter, okay? So this function is nonlinear in X, but a linear in W, and we are optimizing W, so this is the linear function, okay?
Thank you.
Yeah, you're welcome. So it may be a little bit unclear. So I see a comment saying that we are using, we are using a single value X, right? So it's linear. No, this is not correct, okay? So, let's just look at this example, okay? In machine learning, we should consider in a different way, right? So you think about it. These are now constant, okay? So this could be A, okay? This can be written as B, okay? Right, so this could be written as, let's say, something like a times 1, right? We say C, okay? Right, and these are actual variables we are considering, right? So this is maybe AX, BY, and CZ, okay? Right, so equal to D, right? So this is what we are saying, okay? So let's do it here. Maybe that's easier, okay? Let's erase this function. So who can tell me what's this function? Okay, so let's look at this one. AX plus BY plus CZ equal to D. What's its function?
Line equation.
Yeah. This is a plane, okay? So,
oh, okay.
Yeah. So I think you should have learned this, right? So it defines a plane, okay? Look at image. This is a plane, okay? If you use that function because it's a X, Y, Z, right? It defines a plane, okay? So this is when you have, 3-dimensional, okay? So when you have 4-dimensional, it's difficult to imagine, right? So because if you have 2-dimensional, right? So you only have W0, then it's a line, okay? If you have W0, W1, then it's no, 1 is just a value, right? 2-dimensional, 3-dimensional plane, okay? Right. If you have W4, right? So W3, 0, 1, 2, 3, right? So 4-dimensional, right? Then it becomes, hyperplane, right? So in 4-dimensional.
Surface.
Yeah, please go ahead, Deepak. Hello? I think Deepak asked the question.
No. I just said if it is more than 3, this we can say it's a surface, multi-dimensional surface.
It's a hyperplane, okay?
Okay.
It's called a hyperplane. Yeah, but you cannot imagine. Okay, so it's a 4-dimensional case. Okay. Anyway, so if you have something of this shape, right? So you have a parameter and you have a dot product between 2 things, right? It's a hyperplane. Okay. So this is a high-dimensional calculus. It's a little bit more complicated, right? So it's mathematics stuff. So basically, if you have these parameters, which are a vector, for example, right? So you have a vector x. Okay.
Professor?
Yeah.
So I think I'm a little lost. So if you mean by x and x square, so these are all a single variable represented with different powers, or are we talking about multiple variables?
Okay, so the question is very simple. We are talking about single value variable on x, but now we are optimizing the model. X is a constant, right? We see the data, okay? X and Y. So we are talking about W where we want to find the best W so that putting this W there, if you give the X to this function, you get this Y. So W is high dimensional. It's okay?
Yeah.
It's a one-dimensional function to X, but we're optimizing W, which is high dimensional. Dimension is decided by N. Okay?
What would happen if we are trying to learn like 2 or more polynomial functions in the same graph, same data? Like we have x1, x2, and we are still
Yeah,
trying
so this
to
will
learn
be
the
more
polynomial.
complicated, but we need to use simple example to illustrate the concepts. It's okay?
Okay.
Yeah, we will cover these cases later. Okay? Yeah, because the purpose is to illustrate the important concepts in machine learning, like overfitting and underfitting. We're using a simple example. Right? So just for now, don't go beyond this, right? So in this frame, understand everything. That's enough. Okay? Otherwise, we need to jump here and there. Right?
Understood.
Yeah. So basically, here's what I mean. Okay.
Question.
So if you let's see. Right, so if you have Wx, we can say something like this. If you have a vector, W1, W2, let me just make it fast. Okay, W3, I don't want to, it's ugly, so we have to do something, okay. Right, so you have a dot product in this way, okay. And so we are just illustrating you three-dimensional case, okay. Let's do this. Let's just do it k-dimensional, okay. So this is easier, right? So if you do a dot product between, x is here in our case, x is a W vector we are learning, okay? So this could be something similar, right? So once we have something, it's much faster, okay? Right, so this is a linear function, right? So if you have y equal to this, right? This is a linear function, right? So because this dot product is equal to what? Equal to I equal to 1 to k, right? And
Wix.
X, yeah, exactly, right? So this is, right? So this is always a linear function, okay? This is called a linear function. Because, so here the x is our w, okay? So weights are actually, the w weights are actually x squared because they're constant, right? So, if x is 2, then this is 4, right? So so some like this is maybe 2, this is 4, etc. Okay, right? So this is a linear function, right? So because this is a linear form, okay? If you know the optimization, right? If you look at linear programming, if you look at the images, right? So why it's called a linear programming? Because it's all those conditions are those kind of linear form, okay? Right. So these are the linear form. W1, X1, W2, X2, W3, X3, W4, X3. Okay, so we should have something more complicated like this one. Right? So it's all like this kind, right? Weights and plus. Okay, so this is linear form, right? If you have square or something different log, then it's not linear, right?
Okay. So
and if it's difficult to imagine, just to think about three-dimensional W0, W1, W2, then it becomes a plane. Okay, right? If just have W1, W0, right? This becomes a line, okay? Then hyperplane you cannot imagine, okay? Any questions?
Professor,
Yeah.
one of the attribute or you call parameter, what if it's 0? Doesn't matter, right?
Can you repeat your question? What is 0?
The one of the attributes?
This attribute, right? So this is the attribute.
Like one of W's.
Oh, this is a parameter. Okay.
I know, could be 0. Could be.
Yeah, it could be 0. For example, if you don't consider order 0, right? If m is order 0, then you don't have W1, right? So you only have y equal to W 0, right? So this will become a degenerate case, right? So for example, if we go back to here, then although the ground truth is this, right? What you will learn is y equal to somewhere, okay? If y equal to 0, it's here, right? So they're still good or bad, right? So for example, if you guess this line is here, then obviously bad, right? It should be something between here and here, right? W0 is. It's okay?
And Professor, are we fixing the parameters or is it being learned? Like the way?
We are learning this W. Okay, this is unknown. Okay, X and Y are unknown, right? So this is training. We are learning this theta. Okay, in machine learning, we are given X and Y. We are learning the theta. the shape of the function f. It's okay? And after training, theta should be fixed. This model is trained because we have the theta. Then we give a new x, we need to predict the y. It's okay?
Yeah.
Yeah. And in our case, the theta is this w. Okay, we are training. In the training stage, we are learning these w. Okay, using the x and y, which are the constants. Right, these blue dots here, x and y. Okay, and once it's learned, then give a new x. Right, give a new x. We want to guess what is y. Right, because the shape is here. Right. Yeah, I will move on because we have been here for quite a long time.
I have a question.
Yeah, what's the question?
Yeah, in this model, here we have theta is not there. Can we think x? You said x is a constant. Can you say x is as a theta?
Oh yeah. So here's what I want to say. So theta is a vector. Okay.
Mm-hmm.
It's just a notation, right?
Okay.
Yeah, it's not just a vector. For example, if you look at a convolution net or conv net, it's a kernel. It's a matrix. Okay. So it can be any shape. It's just a placeholder. It can be this kind of rectangle. If you later you learn what is right. So what is a convolution? Okay. So it's just a parameter. Well, what's the value of those kernel values inside the rectangle that you slide in the input? Okay. So these are theta. Okay. This is the weight. Basically, this is what you train. Okay. Theta is what you train. Right. Once you train, then you know the theta. Then you put x. Okay. You put x. You know the y. Right. And deep learning models, then you layer by layer, right? All the layers theta are done, then you give the previous x, you know the output, right? Which is input to the next layer, right? So then finally you can go to the ultimate y.
Thank you.
You're welcome. Yeah, next is the concept of error function, right? So why we have error function? Because, you know, you see the y, right? So you see the ground truth, okay? The ground truth is x and a y, right? But your prediction may be here, right? So you predict this curve, the y is here. So you, again, as I said, machine learning is never 100% accurate, okay? So that's why there's some concern from my side on self-driving cars, okay? And so you can do product recommendation, wrong is fine. As long as the majority of times you recommend a good thing, right? The company make money, okay? So there's a difference, okay? So this is error. And we want to learn a curve that minimizes error, right? So if the curve passes through this, then there's no error, okay? The prediction and the true value are the same, right? So we want to minimize the error between them, okay? So this is why we have the loss function, right? So this is basically the previous curve, YWN. Let me see. This is the YWN. Basically, it's the model this one, okay? And this YWN is our predicted value on the curve, right? And the true value is a blue dot, maybe TN, okay? And there's a difference, which is a green bar, okay? So this is just for one data, right? So we have maybe X1, T1, X2, T2, X3, T3, three points, okay? And we want to add all their errors up. Right? So this is this point error, this is this point error, this is this point error, right? We want to make all the errors small on all the data we see, right? If we make this correct, but these two are make a big errors, then we are not actually learning good models, right? Because, you know, it's not working well on all our data, okay? So this is summation, right? So this particular error is very popular. It's called a sum of square error, okay? So the reason we have this is because it's a sum over all the data points. Here we have 3 data points, okay? 1, 2, 3. And for each data point, we have this error here, right? So the difference between this and this. But we square it, okay? And there you may not have to square it. You can also use the absolute values, and this is the length of the bar, right? So here, this is called a sum of the squared error, okay? Let me see. Yeah. Okay, so called the SSE. Okay, you can use sum of squared error, SSE. Okay, this is the sum. This is squared error. Okay, error is this error. Any questions?
Professor, and why are we multiplying with half?
Oh, so this is relevant to optimization. So you think about if you don't have it, it's the same, right? If you maximize this, half is also maximized, okay? Right, if you find that this W maximize this, half is, you know, if originally it's a 1 vs 2, now it's 0.5 vs 1. So this W always gives the best one, okay? We will see why it's a half, okay? Because, you know, this is because, if you take a derivative, right, so let me take something here. Okay. Right, so if you take a derivative of x squared, because we have a squared error, right? So x squared, we should change it to a new line, okay? What's the value here?
It's going to be 2x.
What's the value
2x.
here? Yeah, 2x, right?
Yeah.
Yeah, 2x, not 2, okay, 2x, right? So we have a 2 here, right? So that's why we need to put a 1 by 2.
Ah, okay.
So we will see why we will take a derivative. Okay, so if we have this, then we cancel out this 2, okay?
Then it will be x, yeah.
So this is just a small tricks. It doesn't matter, right? So if your value already maximized, this value, its half is also maximized, okay?
Also, you have mentioned that we are squaring the error, like the prediction minus true.
Yeah.
And if we are trying to square it, so the error is being doubled, right? Like the squared.
Yeah, so it's a square. It's not just double. If your error is 0.1, then square is making it smaller, 0.0, right? Okay.
Ah, okay.
But it's really preventing the case that you fit some points good, but for this particular point, it's really bad. It's 1,000, for example. Then square is 1 million, right? It's a lot of penalty. It will try to put more.
Why are we trying to increase the error? So we can still, without squaring, we can just go with a normal error. But why are we increasing it like by square?
We are not increasing error. So this is if we give this w, according to this squared formula, we will get this error. Okay. We're trying to find a w that in this squared case will minimize this error. It's okay.
Ah, yeah. Okay.
Yeah. So because of this reason, we don't want some green bar to be super big. Let's say 100. Square will be 10,000, right?
Yes, Professor.
Yeah. So basically, if we are now in this scenario, these points are very close. These points are very close, but this is super big, right? So now my major goal, because this item for this point is super big, squared, right? It's 10 squared 100, right? The other like 1 squared still 1. So I should minimize it, right? So I've put most focus on minimizing 100, okay? Maybe pull this line up, okay? So, which we will be changing this W. It's okay? After pull the line up, of course, this becomes small, right? So your answer is, yes, this is basically 2 answers. Is okay?
Yes, Professor. Yes.
Okay.
Thank you.
I see another chat. Yeah, so close square error, just want to close the gap of the worst case, for example, right? But that could be wrong because sometimes this is a mislabel, right? So there's some trade-off. Okay, so sometimes we need a huge loss or something, right? So hinge loss, right? So if we make a small, like a 0.1% error, really big, it's okay, right? If we can make a 99.9 correct, it's fine because this 0.1% maybe, noise, right? Maybe someone mislabeled it, right? Our reading is wrong, okay? So there are different trade-offs. In this case, you assume every label are more or less accurate, right? So you don't have widely wrong labels, okay? T are all relatively close to the requirement truth. Okay, then you can use this. Right? Otherwise, a noise will make this just a shoot. Okay, you are learning the noise. Okay, so here's what you need to take away the message for now. And maybe after the break, because we are running a little bit slow, right? So here's a takeaway message. We will probably just have maybe 5 more minutes, and then we will stop for 10 minutes. Okay. So these are training data you see: x1 t1, x2 t2, x3 t3. Okay. These are the training data you see, right? And the W decides the shape of the curve. We want to pass through all of them, right? Of course, you can use this curve, but it's going to be overfitting. We'll see why later. Okay, but here's what I want to say. If you give a particular shape of like a polynomial of order n, okay, and then you can define those W that makes this particular error the least, okay? Right. So these parameters, W star, are called the optimal parameter. And after the break, we will tell you how to compute it, okay? But just keep that in mind. If we have this ground truth blue dots and we know what model we are using, we have a particular best W to decide the shape of as a parameter of the curve, right? Shape is decided, right? But how it looks like, we can find the best value here. For example, if you give those blue dots here, right? And you say it's just a W0, right? So then it could be here. Okay, this is the best because it's kind of in the middle ground of all those blue points, right? This will be really bad, or this will be really bad. Why don't move up, right? You can minimize the error, okay? Right. Here the error is really big, okay? So you will find, hey, this value is the best for if you order n 0, okay? Then if it's a line, okay, something line, right? So this line is really bad because you have big error, right? So you have the loss function that is squared error, then you will find a way to learn the best line, which is this line, okay? This line is given by that W, right? So AX plus B, or A, B are W0 and W1, okay? And if you say order 3, then and you give those observations, which are the blue dots, okay? Then you will learn this weight parameter gives you this red curve. This is pretty good, right? This is pretty good, right? But this is what I want to say. If you overestimate the complexity model, you say it's order 9, right? So you can twist for 9 times, because if you give y equal to 0, you will have 9 roots at most, okay? If you consider complex loops, right? So in this case, this is wrong, okay? This is seemingly right because for every points in the training data, you're hitting there, right? But we know this is generated from the sine function, okay? So if you see another new x here, okay, right? You're expecting y to be somewhere around here. But if you look at the red curve, because it's overfitting, it makes it so complicated. It's something somewhere down there. There will be a large error, okay? So this is saying that a 3 is probably better than 0 and 1, but still better than 9. 9 is probably not good, right? It's not saying that your function is more complicated, it's better, right? Even if your training error is 0, your test error could be huge, okay? So for NC data, that's useless, right? So these data are what you do training, right? You already know them. You want to see NC data, right? And you want to predict value, okay, accurately. So this does not generalize if you make models super complicated. And after the break, we will see how to find this red curve once you know these green dots, okay? And it's a model shape, right? So like M, okay, for the polynomial. Right? How to compute this red curve. And then we will move on and see whether this model, why it's overfitting, right? So this model is called overfitting because it's not useful, right? Even though the training error is there, right? Here we still have some, here we still have some training error, right? So you see this point is far from still a little bit far from the red curve. But actually this works better than the more complicated one, right? So let me see the time now. Okay, so we will come back maybe in 6:20. Okay, so let's take a small break. Yeah. Thank you. Yeah, I see a comment by Deepak, right? So you did not hear anything? Can you hear me now?
Yeah, I hear now. There was a problem.
Okay.
It's okay now. I think my internet has some fluctuation.
I see. Okay.
Okay, thank you.
Yeah, we will come back maybe a little bit more than 10 minutes. Okay, yeah. Okay, let's begin. Right, so here I plotted the parabola function, right? So y equal to x squared. Okay, so let me ask you this question. What would be a derivative here? Let's say if this point is 1, for example, what will be the derivative here? So what will be the derivative dy by dx?
2x. Wait.
Okay.
Get to 0.
2x. Okay. What is x here? It's 1. Okay. 2 times 1 is 2. Okay. So derivative here is some positive value. It's okay. 2x because x is positive. It's okay. Right. If we have a negative value here, so the derivative will be negative. Okay. Because it's a -1, then this becomes the derivative -2. Okay. Right. If we are here, put it 0, then because x is 0, 2x is still 0. Okay. So this is saying that if your derivative is 0, okay, so you are kind of flattened, right? If a derivative is you are on this side, your derivative is positive, right? So if you continue along the positive side of the x, you will increase the y, okay, right? And if you are here, and because this is negative, right? So if you move on the negative side, okay, because it's -2, okay, move on the negative side, right? So you will again increase the y. Any questions? Moreover, you can see the curvature, right? The curvature is larger. Okay, so this is flat, and the gradually increase very fast, right? So if you look at 2 here, okay, what will be the derivative here? For x go to 2, what will be the derivative?
4.
4, yeah, 2 times 2. Okay, this 1 becomes 2, right? And then this becomes negative. So this means if your curvature increases, right? So the the speed up also increases, right? So this basically tells us, let me clear a lot of those things, okay? So this is basically telling us that, basically derivative is just the how, like the tangent, how the curvature look like, okay? If this is big, okay, this is small, okay? And this is 0, okay? And this is then negative small, because this is negative big, okay? Right. So and the derivative always moves in the direction that increases your your value, okay? So we will see later. So for some functions that are relatively complicated, you cannot have a closed formula, right? So you don't know where let's say y is the loss function, you want to find the minimum y. You don't know where to go, right? So you can go so-called a gradient descent, which means this is the gradient, right? So this is ascent direction, which increase your error, right? So you can go the negative direction, okay? But initially you will go very fast because it's a 4, right? And then this 2, you will go slower, right? Here it actually becomes 0. Finally, you will walk to here very close. Okay, this is for the case that you cannot find the close formula, right? So you can, but you know how to compute the function x and y, right? So you can go here and compute a step, and then go here, compute a step which is smaller, and compute here, and again smaller. Finally, you reach the minimum value. Okay. But here we are looking at a more straightforward solution if you know how to compute it. Okay, so in our solution, it's simple. Where is a place y is the smallest? How to compute it? Anyone have any solution? Hello?
Professor, can you please repeat the question?
So where the value y is the smallest? How can we compute the smallest y and find x that y is the smallest? Okay.
0.
At 0. At 0.
Yeah, 0, right? So the reason is very simple, right? So if you take a derivative of y to x, okay? Right. And set it to 0, okay? Right? You will find the value, right? So if the 2x is 0, then x is 0, okay? It's exactly this point. You don't need to do any gradient descent, this kind of thing, okay? Because you can directly take a derivative set to 0. Any questions? Okay, so this is only valid if your function is convex, okay? if your function is convex, this shape. If it's concave, what you get after take a derivative 0 is a maximum, right? Oh, sorry. So I think I should share my desktop. Right. So you see this is a concave shape. And if you get x equal to 0, you get the smallest value, okay? If you have a this is a convex function, okay? If a concave function, it's a maximum value, okay? If your derivative is 0, right? That's a flat location, okay? So what is concave, what is convex, right? So this is totally wrong, right? So this is right, okay? Convex means if you put a line into any two, excuse me, any 2 points on the curve, okay? Right, it's above this curve, okay? Concave means for any 2 points on this curve, if you put a line, it's always below this curve, okay? So this is concave, right? So yeah, so you say that we are talking about only one x and one y, right? So in machine learning, we may have multiple x, right? So this is more complicated. This goes to the multivariate calculus, right? But again, this is the same, okay? Let's look at this image here, okay? Right. So this shape is a convex shape, okay? So how to compute this convex? We will discuss it later, okay? So basically, you consider the second order, which is the Hessian matrix, okay? And it's a positive semi-definite, but we will cover that later, okay? Don't, it's getting maybe too much, right? So yeah, let's take a look. So basically, you know, this is maybe, in our case, I think we don't see the x and the y, right? So you just know that this may be x, okay, and this may be y, right? And we want to minimize there. And now we have 2 input variables, x and y, x1, maybe x2, okay, and this is y, okay. Right. In this case, what you do is your model, right? Y is a function of x, right? You take a derivative to x and set to 0, and to x2 also set to 0, right? In this case, you know this point is the smallest, okay? Right. It's exactly this point where along every direction, it's actually the derivative 0, okay? So again, a lot of cases, if you take the derivative, it may not have closed formula, right? In those cases, you have to do gradient descent because you cannot compute the value, right? In a lot of cases, you can exactly compute where is the location where we can achieve the minimum error, okay? Or, you know, so by the way, this is not y, this is error, okay? So this is more like your predicted y value and the true y value different, okay? It's more like a sum of squared error, this kind of stuff, right? And you want to find those weight matrices, okay? Right, so this is W1, W0, okay? This is, in our case, it's not the x, y, okay? So basically, we are talking about an error function with respect to theta here, okay? We are not talking about this x, because our model is training theta to minimize the prediction error. Okay. What am I doing? So, and this only holds if your target function, the loss function, is convex, okay? If it's not convex, this does not hold. Let me give an example. Even for like a one-dimensional case, right? So, you know, so you cannot say, hey, this is the max value, right? Because maybe here you have an even larger value. You can also not say, hey, this is the minimum value, right? So because here you can see the minimum value. Because this is not convex, also not concave, right? So here, this line is below here, but if you put these 2 lines, this is above the curve, right? So this is not convex, not concave, right? So then you don't have this property where you take derivative 0, it's always the minimum with respect to the target value. Okay, so convexity is a very important concept before deep learning. Right? After deep learning, everyone just do gradient descent. Right? So, and it actually works in reality. Right? So we will go a little bit deeper in these concepts because it's a fundamental course. Okay, so okay, let's continue a little bit. Okay, now we are here, right? So we just described that if you define your loss function. This is the function, convex function. Okay, we will see why it's convex later. Okay, and if you define this loss function, which is the function of w, right, and then you take a, you know, you want to find the w and minimize this error, right? So what you do is very simple. Okay, because you know the y equal this thing itself is a function of w, right? So just take a partial derivative of this e function. Okay, this e function, take a partial derivative to each of them, right? W0, and then take a partial derivative to W1, and then take a partial derivative to W2, take a partial derivative to Wn, and set all of them to 0, right? If you can compute these these W values that satisfy this requirement, right? You can set them to 0, right? Then this is where you achieve the minimum error. Okay, any questions so far? Because here we are a little bit more complicated, right? So previously we talked about a two-dimensional hyperbolic, right? So parabolic, right? So now we have m plus 1 dimension, right? We will start from 0 to n. Okay, so this will be a little bit more complicated, but just to set all of them to 0, right? So then we will get the closed form. Okay, so let's take a look at how this is calculated. So in the document, we actually have the files for you, and it's called the node. Okay, so here's what we have, right? So this is our polynomial function. Okay, right? Maybe we should just stick to here. This is our polynomial function, right? And if you want to look at the error, maybe the error is clearer. Okay. So this y is just this y. Okay, it's a polynomial function, right? I want to minimize this error. Okay, and it's a function of w, right? Okay, because y has a w, and xn and tn are constant, by the way, once you have the training data. Okay, these are xn, and this is tn. Okay, now what we do is for each of those, this is a vector, right? For each of those wi's, right? So you have n plus 1 of them, you take partial derivative. Okay, and for each of them, you want to set this to 0. Okay, that's why that's where you get the smallest value, right? And for this purpose, what you do is you just take a derivative. Okay, so you take a derivative over this thing, right? So here we go back to what you should already know in calculus. So these two rules. Okay, let me see why. These two rules. The first rule is if you have fx and gx plus together, take a derivative x. It can be considered as fx, f take a derivative x plus g. Basically, this plus can be taken out. Okay, so this is the first rule you should know. The second is called the chain rule, right? So if you have partial f to gx, right, it's an embedded kind of function, right? So then you can first take a f to g, right, and then g to x. Okay, so this is called chain rule. So in our case, if you go back to here, right? So now you want to take this thing, take the derivative to a particular w. Let's say w1. Okay, w2 for you. What do you do? Let's say this is w2. Okay, right. So the first thing is that you will take the sum out. Okay, so the sum is taken out. You just take a partial derivative to each of this item. Okay, because the sum can be taken out. Right. Secondly, you need to notice that, for this item, it's a function of what? It's a function of y, okay? And y itself is a function of w, right? So this is what we are doing. Okay, so basically, if we make this, okay, so I just keep the notation simple, right? So w1, right? So then what we have is actually maybe w2. So maybe we should still use this. Right. So why is it looking like this? So we are having this, okay? Yeah, maybe let me finish typing it so that everything becomes clear. Partial to y, and y, take a derivative to vector w, maybe just w2. Okay. What's wrong here? So, let me see what's wrong here. Just one moment. I think there must be some notation error. C dot fraction is on this side. Yes, this side is correct. And this side must have something wrong. Oh, okay, I see a bracket here. Oops. Okay, just let me retype it. Okay, so so what we have is actually we have the error function, right? So this E. Okay, so this is our error function E. So can you hear me clearly?
Okay.
Yeah.
Okay.
Yeah, you sound just fine.
Okay, because I just switched to another microphone. Just want to make sure everything is fine. Okay. All right. So basically, this is a chain rule, right? So your error function is the actual function of y first, right? Then y can then take derivative w2, right? So this is what we have here. Keep in mind this function, right? This is chain rule. Okay. First e, it's a function of y, and then y the function of w2. Okay. Now here let's go.
Why are you dividing by W2?
What?
On the left side, why do you divide by W2?
Y is function of the.
Oh no. So sorry, I missed the partial. Okay, so yeah, it's this one. It's okay. It's chain rule.
Okay, yeah, I gotcha.
Yeah. So this is what I want to say, right? Yeah. Okay. Now you see this y, right? First we want to take e to the y, right? So if you look at this part, this is really a function that is a y minus a constant, right? So okay, so this is the first part. Okay. If we take the derivative y, right? So now we are doing something here, right? So we take a derivative y, e take a derivative y. What will be the result here?
And I have a question about
Okay, yeah, go ahead.
Tn. Tn, you said it's a constant. It's also a constant value of y, right?
No, Tn is a constant. Y is a function, okay?
Yeah, but the Tn should have some relationship with this, right?
No,
That's how
you see here, this is training data. This is x, this is Tn. It's okay? This is for n data point, okay? Yeah.
Mm-hmm.
So this doesn't matter, right? So x n is y, so this is 2y. It's okay? X squared take derivative x is 2x. It's okay?
Wait a minute, would it be 2 times in parentheses y minus Tn?
So this is what I want to say. So x squared take dx is 2x, right? Is this acceptable?
Yeah, that's cool.
Yeah. Then we have x minus a constant, which is Tn, right? Square divided by dx. It is still 2x. Is this acceptable?
I thought it would be 2 times x minus c.
Oh yeah. It's just 2 times Tn. Sorry. Yeah. Sorry. I mean this. Right. Is it okay? And then you in chain rule, you further take this derivative of x minus c to x, right? This is just 1, okay? Because c is a constant. So this is 2x minus c, okay? Any questions? If not, so basically, this is saying that the first part, we take because we treat it as y, then we take this thing. What we have is twice this term, right? This 2 becomes 2x, okay? Twice this term, right? And because it's a constant, take the chain rule. The second time is x minus a, take a derivative of x is 1, okay? So, okay? And then we have this 1 by 2 takes into the sum, right? Cancel with this 2, right? So this is y we actually, we got the first term, right? So we get this first term, okay? So this first term here is this term, right? And we just take this 2 inside, and because we take a partial derivative, this 2 cancels with 2, okay? And then we have twice this, but we have a 1/2, so we cancel, okay? So we got this term, right? This is the first part of the chain rule. The second part chain rule is y to w2, okay? Right, so what is y? Maybe this will be clear, okay? This is y, right? And w2 is here, okay? Then take a derivative w2 is x squared, right? Okay. So this is I, take derivative of I, xi squared, okay, for each I. The relevant constant is x to the power I, okay? So this gives you the second part, right? So the second part of the chain rule is y to take derivative w2, okay? Right. So this gives you x to the power I, right? Because, for wi, this term is x to the power I. Okay, so this becomes this. Any questions? So put simply, this is a chain rule, the first part, the second part, okay? Basically, it's the first part, here's the second part. Right? So just in case, in the future, I will just make it really quick, okay? Because the first time, and a lot of people may forget chain rules, so I just recap a little bit, right? So now, because of this, you can time this inside, right? So, so firstly, this thing is this thing, right? So you pull it here, you get this, okay? And then the second thing is you set it to 0, okay? When you set it to 0, this minus, you can move this right-hand side to here, right? So basically, this part is equal to this part. So we get this, right? Of course, this summation should be associated with both sides, okay? And now, finally, let's look at what is this, right? So keep in mind, those x and t are constant, okay? The data you see, this x, this is t, okay? So this, on the right-hand side, this is a constant, right? On the left-hand side, right? On the left-hand side, this is what? This is not constant, right? But we have j. This is the linear equation. Okay, this is the linear equation with w0, w1 all the way to wn. Okay, right. So this is a linear equation, right? So we have how many such equations? We have n+1 such equations because we are taking partial derivative w0. We get a one equation like this. Okay, then we can take partial derivative w1, take partial derivative w2, partial derivative w3, etc. Right. So this is what we get. We will get n+1. Okay, because we have 0 to n, not 1 to n. Okay, we will get n+1 equations. And what we want to do is we want to find those w0, w1, w2, w3, wn that satisfy all these n+1 equations. Okay, so we have n+1 variables of w, right? So this becomes a linear equation, right? So this becomes something that you should already know, quite well. Right? So, you can use like a Gaussian elimination or those kind of, easy method to calculate. Right? So this kind of equation, right? So you are getting this, let me see. Basically, you are getting this kind of equation, okay? And where x, y, z here are just the w0, w1, w2, okay? And the other are actually derived from the data, x and t, right? And you have 3 equations, 3 variables, then you get a unique solution, okay? So that unique solution, once you solve it, it's actually the optimal w, okay? So this is what we have here, okay? So you just solve this, because each equation is from 1 wi. We have n+1 such equation, okay? And we have n+1 w's, right? w1 to wn, 0 to wn, okay? Then we have a unique w star that satisfies all these equations, which means along every wi direction, it's 0, okay?
Do you have n+1 terms on the right side also in this equation?
What do you mean by n+1 on the right hand side?
Because for this equation, right side also should be n+1 terms, right?
You are talking about this equation?
Yeah, the equation here. Yeah.
Yeah. Oh,
This n goes from 1 to n, tn xin, right side of this equation.
Yeah, you mean this one, right?
Yeah, right.
Of course, you know.
It should have
this
m plus
thing
1
is together, right? So is this okay?
Mm-hmm.
So you time this with this, and you time this with this, okay? But this thing is itself summed for n times. It's okay?
Mm-hmm.
Yeah, so it's on both sides when you move this thing, right? Okay?
Okay.
Yeah, so there's a note,
Okay,
you can take a look yourself. But anyway,
Mm-hmm.
even if without it, it's a constant anyway, right? So this is W0 to the, M and right? These summations, they're just constant, okay? They're the weights of the W. It's okay?
Okay, thank you.
Yeah, you're welcome. So anyway, so you can either use the inverse matrix or the Gaussian elimination, you will get this. Okay, so then these W's are what you have. But we have one story that is not complete yet, right? So this should be what? This should be convex, right? If it's not convex, so let me see whether we still have that. That's so let's search for our okay. Only when it's convex function, right? So then you can, for W0, W1, W2, every direction is 0, right? And it's the lowest point, okay, of this function. Right? If it's not convex, you do not have that, right? So now the next thing we want to show, let me see. So, yeah, so I think there's a question that is directly relevant to this, right? We can do this because it's a convex function, which means this function, this loss function itself is a convex function, right? How to see that, right? So this actually, there are different ways to prove something is convex, right? So in order to do that, there's a book by Stephen Boyd, right? So convex optimization, okay? And you can freely download it, but the problem is not freely downloaded because it's maybe 600 pages. And you can take a look at that. So basically, I think any people do optimization, this is the basic because they are still non-convex optimization. Right? So, but this is super complicated. If you have interest, you can read this book. Right? So a lot of mathematics and matrix operations. Like this is positive semi-definite. Right? So this kind of all these complicated stuff, right? So here we are just touching very superficial part of this, right? So if you are interested in doing deep machine learning, right? So you are doing like publishing papers in ICML or NIPS, that book you have to read it. Otherwise, you probably what we have here is enough because you are just learning the basic machine. Okay. So what we have here, there's a something from this link. Called positive way, convexity. So this is a few operations that preserves convexity. Okay, let's search for so this is a slide for that. Okay, so here you can see that a few operations. This is called the convex algebra that helps you immediately see whether a function is convex or not. Okay, I think I will skip this just to look at what we have the screenshot here. Okay, so firstly, if your f function itself is convex, right? Your alpha f is also convex if alpha is positive. Okay, so this is the first thing, right? Non-negative multiplication is convex, right? The second, if you have two convex functions, their summation is still a convex function, right? Finally, if you have a composition with affine function, let's say you have a affine function. Affine function is just a linear function, but this is more complicated because x is a vector, A is a matrix, right? It's a high-dimensional extension of X plus B. Okay, B is a self vector, right? It's called affine. Okay, the difference between affine and the linear is because sometimes people call if B is 0, it's called linear, right? If B is not 0, you have a bias, it's called affine. Okay, so it's just a linear, right? It's a plane for them in high-dimensional space. Okay, because X could be X1, X2, X3, then it's three-dimensional space, right? And so if you have a linear function, right, associated with an f, right, and the f itself is a convex function, right, and this is a linear function to some variable, okay, then this whole thing is still convex, right? So I think keep these three rules in mind, you already can solve a lot of problems, okay? For example, let's look at this error function, which is essentially this error function, right? How can we see it is actually an affine function of W, right? So the first thing, you need to know is this is linear, right? So this is where we actually told you guys. This function is linear. Okay, let me see where it is. Right, we were talking about this is linear to W, okay? Not to X, but to W, right? So this is really a linear function to W, right? So this part is fine already, okay? Of course, if you minus something, it's still unfine, right? It's still, plus B and this identity function, right? So it's still, unfine, still convex, okay? So affine function always convex because, this is the line, right? It's both convex and concave, okay? If you think about plane in high dimensional, it's also both convex and concave. It doesn't change the convexity of your function, right? And now we already solved this thing, right? The next is after square, whether it's still convex, right? So this is the question, right? It's true, right? So x squared, this function f is x squared, right? This function also convex, okay? Because, if you take first derivative 2x, take the second derivative, it's 2, right? 2 is positive. This is called second derivative, right? If your second derivative is positive, it's convex, okay? Otherwise, you can also see, any 2 is always above this, okay? It's convex, right? And x squared is always convex, just keep that in mind, right? So now you have an alpha function associated with another function f, which is square, which is convex. So this term, let me make it, okay? Then this term itself is already convex, okay? Finally, we take the summation, right? So because each term is convex, take summation is still convex. We are using this, right? So finally, we are pretty sure that our loss function, so this EW, is a convex function to W, right? And that's why, because it's a convex function to W, that's why we can then set those things to 0, right? So we set every of these to 0, okay? We will get the minimum. And also, we can get a closed form formula for W, okay? If we cannot get it, we have to use gradient descent, step by step, go to the small value. It must be there, okay? It must be somewhere there, but you cannot compute it, right? So you have to try and move, finally reach it, okay? This is where you get gradient descent, okay? If you can compute directly, you don't need to do that, okay? Any questions? So that completes how we find the, how we find those red curves here, okay?
Hey, if the second derivative is negative, is it concave?
Yeah, exactly. So, the negative convex and concave. So this is something, second derivative convex. Okay, so this is something in calculus, right? So, anyway, so second derivative curvature, right? So this is what we have. Okay, so this is in calculus. Okay, if your second derivative is positive, then it's convex. Okay, if your second derivative negative, then it's concave. Okay, so this is a second derivative rule. This is not what we will be teaching, right? It's in calculus, but if you forget, you can recap. Okay, and if your X is high dimensional space, then this becomes a matrix, second derivative of the matrix. Okay, it's called the Hessian matrix, and this becomes a positive semi-definite. This is called negative semi-definite. And don't worry, we'll cover that. Okay, so yeah, that's why we will have to go back to the one-dimensional case here, right? So it's simpler. Okay, let's continue if you have no questions. So here what we want to say is that if you have those blue dots, and you can compute this red curve, right, analytically in this example. Otherwise, you can use gradient descent, right? So you can reach the optimum. Okay, and if it's not convex, oftentimes we can still get a good value. That's why deep learning these days are okay. Okay, because we keep going towards the downwards, right, along the loss function. Maybe you can get to a reasonable value, may not be the best. For example, if you have a function, something like this, okay? Right, so it's not convex, right? So maybe you do not get a minimum point, but you are here. It's equally good, right? So because you know your loss is already low, you make small mistakes here, okay? So why not, right? So we can still use it. This is why deep learning these days are using, first order methods, and it still works, okay? You just need to find a good point. It's never 100% accurate, right? So optimal is maybe 99, and you are 98 accuracy, but it's fine. It's usable, okay? So this is where deep learning plays a part. it's deep learning models are mostly not convex. Okay, and so yeah, finally we have the root mean square error, right? So remember we have the sum of squared errors, right? So if we go back, we call it a sum of squared errors. Okay, usually we don't need to include this. The reason we include this is to cancel this when I take a derivative. Okay, and this is SSE, sum of square errors. Okay, and there's another concept called the mean square errors, MSE. Okay, and this is saying, hey, I will divide by n. Okay, because it's a summation of the green bar squared for all the points, right? The problem with sum of square error is that, you know, in computer, each number has a limit, right? So it's 4 billion, right? For example, for 32-bit integer, right? But the summation could go beyond that range. Then you get to trouble. Okay, right? If you take the mean, it's always making sense, right? It's just a green bar, an average green bar size. Okay, so but it doesn't change the results because this n is the number of training data you have. It's a constant. Okay, you maximize the sum, you also maximize the average. Okay, or minimize because this is error. Okay, so it's the same thing. Okay, it's just that you want a numerically more stable. You divide by n. Okay, this is mean square. And then now we know that if you take divide by n, it's a mean squared size of the green bar. Okay, it's because we still have the square, right? So here we say that we can go one step further, right? Ignore this 2. Okay, this 2 is because we divide by 2, right? We cancel it, right? So assume this is sum of squared error. We divide n, then this is average green bar squared. Okay, now we take a square root, then this is average green bar. This is like average error of a data point. Okay, so this is called the root mean square error. Okay, so this is usually these days people write it like root mean square error. Okay, RMSE. Right? So you can see these relationship of those terminology. Unfortunately, I have to get control of my mouse this one. Yeah, so let me use pen. Okay, so we have sum of squared errors. Okay, and if we take divide by n, we get a mean squared errors. But each data item's errors, average errors, is still squared, right? So then we take the root, then we get root mean squared. This is usually for the regression, by the way. Okay. Usually, if you don't want to report the error, like making it like in the magnitude of the green bar, then you just let me clear this. Then you don't need to take the root, right? So the square root is taking time. Okay, you just minimize the mean squared error. That's fine. Okay. If you want to report the error and plot it, right, it's better to make a human readable value, right? So this is the actual error, average error. Okay, then you can do this. So in our previous case, we have seen, for example, let me see the time to make sure we are on the right track. Okay. Yeah, we are a little bit slow, by the way. So in our previous case, we see 0, 1 are not very good, 3 are pretty good, right? And 9 becomes very poor because you can predict very wrong values from the green map. Okay. So yes, if you look at so we usually have training data, right? The training data actually decreases and finally to 0 because it hits every blue points, right, in the curve. But when you test on some data that is not there, right? So actually the error is huge. Okay, it's shoot up. Okay, maybe from 3 to 8, they are all okay, but 9 is not okay, right? So you know, on the training data, the blue dots are all on the red value. Okay, so the difference from the predict value and the true value is 0. Okay, but if you have some holdout test data, okay, then the true value and the predict value is a large gap. And if you look at here, this is an even huge gap. If you are here, right? So this is not good, right? So this is usually our curve is looking like, right? So this is almost always the case. Your training error will be smaller because this is where you learn, right? If you are optimized on the data you see, of course, the errors tend to be smaller than on the data that you don't see, okay? But if you overtrain your model, right, or make your model overcomplicated, it does not generalize. On unseen data, your error will increase, okay? And that's why you know, you should stop, okay? You should not use this parameter, okay? don't go that side. Maybe this side is good, right? Because for example, if you have 3, 4, 5, 6, all have the same value, you will take the smallest, okay? Because it's simpler. You only have W0 to W3. Right? Here you will have W0 to W8. It's more complicated, but it's the same in effect, okay? And potentially, the simpler model, the better. We will see that later, okay? Another slide. Yeah, here are those 4 curves. If you look at the W values, right? If we only have W0, we have this value, which is really small, close to 0. Basically, we have this curve, but our curve is here, okay? 1, then we have these 2 values. And 3, we get this value. But actually, our error becomes very small, right? Better than 1, okay? But what if you go too much, okay? You go to n, to 9, right? So then you will get those big values here, okay, all the way to here. So you can see why, right? So if you go back to this example, you're changing quickly here and here, right? So the reason it's changing quickly because those weights are big. It can make the curve very unsmooth and has looking just not right, okay? So basically we say that m equal to 9 is not good value because these actually are values that make your training error 0, right? Using our previous optimization function. But this is not that good, okay? Because these weights are big. So by the way, so if you, let's say, so here, still nice order, but we can make it a little bit better. Okay, for example, if you go back to here, if we only have 9 points, you will get really poor data, okay? You will get really poor data. But if you increase to 15, then it's kind of correct you, right? So if you have a point here, it will not go too much down there, right? It's already better, okay? If you have lots of data, okay? Then every data will correct you and cancel each other's bias, right? So finally you will get a pretty good. This is even better than the 3rd order if you only have 9 points, okay? Right. So this says that if your model is complex, but you have abundant data, it's also fine, right? This is actually what's happening with deep learning these days. The model has tons of parameters and it needs tons of data. Okay, so if you look at a curve, so let me give you an example. Data keeps improving deep learning. Okay, so here's a typical like argument about why deep learning is good, right? So if you have lots of data, okay, right? Your other models initially perform better than the, red is above blue, right? It performs better. But then if you give more data, it just stops there, right? Because the assumption is too simple. You cannot fully utilize data. Right? Your deep learning initially is end-fitting. Okay, we'll see what is end-fitting. Model is not good. But if you give more and more data, it just keeps improving and get to very good performance. Okay, so but we are learning the old models, by the way. Okay, so but again, the rule fits because we are building a MEMS site for you guys, right? So if you have lots of data, complex model is okay, right? Right. So all right. So then yeah, so we see here that if you only have 9 points, these values can get really big, right? And we want to avoid that, right? So what we can do is this. So we can add a regularization function here, right? So what means that now our optimization is trying to minimize this error, right? Find the W's that minimize this error. If we really take the W's themselves also into the error function, right? If your W is big, let's say this term will be big, okay? If this term is big, then your WE will be big. Then you will try to find the W that is making this small, okay? For example, if you look at here, these values are big. Then definitely this will not be the best point for this E title, right? Because E title also has a second term. And those values just will make the error super big. And then we will try different W, right, to find a balance between, okay? So by the way, so this is the vector length notation, okay? This is a vector length notation. So what I mean is this, for example, let's go back to here. Yeah, I'm not sure whether this is a good way because it's kind of slow, right, to type, but let's see. So basically we have W. So we should use, so we can, so so we are using, you know, board face, right? So BF, okay, board face. This actually is equivalent to, you know, these days people try to use a board face to mean a vector, okay? It's equivalent to if you use a vec W, okay? Right, so basically we are talking about W is a vector, okay? So what is this? This is actually equal to, I think, maybe SQRT square root of, you know, W1 square plus dots plus WK square. Okay, so this is it. It's okay? So this is just a vector length, right? So you know, if it's two-dimensional or three-dimensional, it's very simple to see, right? It's just a vector length, right? And this is called a two norm, okay? Yeah, it's the norm of the vector. This is two norm, okay? It's the length of the vector, right? So so this is the notation. When you take the square, you see this square here? When you take the square, okay? Let's see, we have a square here, right? So then what we mean is we just take out the square, okay? Is okay?
We only use two norm?
No, you can use any norm. They have different effect. This is using two norm to regularize, okay? You can also use L1 norm. This is L2 norm, okay? Yeah.
Yeah, sometimes we use the Frobenius norm, right? For the matrix.
Yeah, you
case.
can use Frobenius norm for matrices. Yeah, I can explain it a bit shortly. Okay, so here you can see that this W becomes super big, right? If you have a W, you use this norm, and the sum W becomes that value, square is super big. Okay, right? So you definitely, if you want to minimize this E, you will not take a W like this value. Okay, this square is just crazy. Okay. Then you will find some W that will make it a little bit large, but you will not make this explode, right? So this is called a regularization. And how much importance this regularization plays is adjusted by another hyperparameter defined by human, okay? The lambda. You can try different values and find the one that works, okay? Yeah. So a student also asked about Frobenius norm. So let's take a look at what is Frobenius norm, okay? Yeah, I think we can just look at the image. It's always more helpful. Okay, yeah. So because we have more choices. So this is Frobenius norm, right? Basically, you have a matrix, every element squared, right? And then you sum by row and by column. Basically, you sum every element squared, okay, in the matrix, right? And then you take square root. This is called a Frobenius norm, right? In case your weight is a tensor, for example, then you can use Frobenius norm, right? Matrix of tensor, right? Just a square every element, right? So in our case, it's a vector. If you use L2 norm, it's also square every element, okay? So maybe people are telling you that they are using Frobenius norm, or they are using L2 norm, right? And sounds crazy, right? So it's very simple, because if you square it, right? Frobenius is square, right? Take out the Frobenius norm, right? What you get is every element square, okay? For regularization, that's just that simple, okay? Any questions? Just your weight matrices, everything squared. And this is for regularization. I see a student ask why we do regularization, right? Yes, this is where we are getting to, okay? Now, if you do regularization, even with just 9 points, you can get this point, this line, okay? On the left-hand side. Because we have a regularization value, okay? If you don't have regularization value, you will get this one, okay? On the lower left corner, lower right corner. If you have a regularization, you will get this value, right? Because you have lambda. Why? Because you will not take, if you use this regularization value, you use this weight of matrix value, which are these values, right? You think about this may be W6 squared, right? Let's say because we have this, right? WX6 squared, right? So what will give us is this, right? So this explode, right? It's super big, maybe 10 to the power 12 or something, okay? Then this is not the minimum value, okay? While our optimization tries to minimize this error, right? We will not take this W here, okay? We'll not take this W. We'll take a more reasonable W, which are these Ws. Okay? And because we add the regularization, then it will strike a balance between not exploding W and also minimizes, right? So of course, if you just look at this error, it will be increased a little bit, but that's not bad, right? So if you try to push the training error to 0, this is the curve you will get, okay? So this is try to find a middle ground at the regularization to improve your generalization, okay? Your model will generalize, okay? Any questions? I mean, I think Harris, right? So Harris asked this question. Is this okay, Harris? Yeah, okay. I also see another student ask me the norm of the vector. Norm is more like the absolute value for one value, right? For you know, it's the magnitude of a vector or a matrix, right? So if you have a single value, it's like absolute value. -5, take an absolute value of 5, right? If you have a vector, then L1 norm, L2 norm. L2 norm is the length of the vector, right? If you have a matrix, then it's a Frobenius norm, right? So there's also other matrix norm. So these are the mathematics stuff that we will expound later, okay? So, so yeah, student ask whether this is a convex or concave function, right? So this is a good question. It's a convex function, right? So why? So if you look at here, right, we are for each W, it's you know if you look at this function, right? So this is f W vector, right? Is equal to what? Is equal to W1 square, right? Okay. So this is this function, okay? And this is another function that's a WK square, right? So each of them obviously is convex, right? If you take second derivative, it's just 2, okay? And now the summation of convex function is still convex, okay? So the norm is always convex. Keep in mind, any norm is convex, okay? This is how you define norm, okay? The magnitude, the norm is always convex. Now that because, now we know that this part is convex, right? And we have proved this part is convex. Some of two convex functions is still convex, right? That's why we can use an old trick, okay? Still to take the partial derivative W0 to WK, n, okay? And then, of course, this will change a little bit because, when you take partial derivative, the formula need to change accordingly. Let's say you take partial derivative W1, right? You will have 2 W1 afterwards, right? So the linear equation will change a little bit. Okay, so this will change also your W values setting. Okay. Let me see. Yeah, so I see it's answered. Okay, so if I haven't answered your question, because it's difficult to take a look at chat easily, right? So if you have any question, you can unmute yourself and ask directly. Okay, otherwise I may miss your question. Okay.
Excuse me, Professor, I have another question here.
Okay.
I wanted to get some intuition behind the regularization function. If you see the right part lambda by 2 into norm of, L2 norm of the vector W,
Okay.
assuming that we need to decrease, in order to decrease the error, we need to, what is this regularization error is saying that?
No, so regularization just to avoid exploding, okay?
Decrease the weights, smaller weights would be decreasing the error.
No, it will generalize, okay? Improve your generality, okay? Because if you look at here, your error is 0 on the training data. It's okay?
Mm-hmm.
Yeah, so, but you don't have the regulation part. Of course, the W will find this one, okay? Right? Because you are order 9 polynomial and you only have 9 points. You can hit every point, okay?
Mm-hmm.
But this is not good, right? So the reason it's not good is if you look at their weights, right? It's super big, okay? It's something like this, right? And now that's why it motivates the regularization. Okay, it works in general and just help your model generalize. Okay, even if you are in this scenario, if you add a generalization, you will be here. You will be here. Okay, it's still okay. It's okay.
If we use higher order polynomial or anything higher, then we need to get into regularization.
Yeah, if your model is overcomplicated and the test error is low, then you try normalization. It will work. Okay.
Okay. Okay. Got it.
Yeah. So that's basically what we are talking about. So it's just one example, right? So in deep learning, the dropout and those kind of different techniques, right? So they are all for this kind of purpose. Okay. So this is one way to do regularization. The simplest way is add a norm for the parameters. Okay, it's for the theta, right? And the parameters norm. Okay. So this is just a intuition here. And one thing that we haven't talked about is lambda, right? So the lambda, if you take extreme values, it will not be good. First, the first extreme value is 0, right? 0 means we don't have regularization. Then we go back to the previous case, which is not good. Okay. The second case is what we make the lambda super big, right? This is also not very good. Maybe we make it 10,000, right? Why this is not good? Because now this weight is so high, then this is not important at all, right? So we just give a 0 vector, W0, W1, everything is 0, right? Then because this is so important, then we basically will cut everything to close to 0, right? And this is also not what we want, right? So this is corresponding to this case, right? If we have a very high weight, then we cut everything to 0, then the second part, the regularization part, will be low, right? Error, okay? And the first part is not important because our weight matrix weights to the second part is really dominating, okay? So you need to find a good one, right? So if it's 0, then it's not effective, right? It's not doing any regularization, okay? And so here we are using lawing, right? So the reason we are doing lawing is because if you look at the lawing function, right? So this is the lawing function, right? Lawing is log E, by the way, right? So the natural log, okay? Log E, not log 2. But it's the same thing, right? So basically you pass through 0, 1, or 1, 0, right? X is 1, Y is 0, okay? And now we are saying our weight, actually, if you are here, right? Then basically, so if your lambda is 1, it's actually quite a big value, okay? So if you think about lawing, it's 0, right? Well, if your lambda, how to say this? Your lambda becomes a very small value, let's say negative infinity, okay? So here, let's consider, how to say this? This is x, right? Lambda is lawing x. Y is lawing lambda, okay? So when y is negative infinity, right, goes to negative infinity, your lambda is actually 0, okay? Right. When your lambda goes to 1, your y actually pop up, right? So you pop up, finally pop up to 0, okay? So that's why we are using this scale, right? So this is more sensitive, right? So some value from 0 to negative infinity, right? It's negative 18, negative 32. You have a feeling of 18 or 32, okay? Basically, it's saying if my lambda is moving in this range, okay? My lambda is moving in this range. I can report the lawing value, which is in this range, which is more descriptive, right? Otherwise, you are saying 0.22 and 0.21. You don't feel it. Yeah.
Is there any criteria to determine what's the suitable lambda, or we have to just be smart?
You try. Okay, it's called a cross-validation. You just try different lambda values, right? And then see which one works the best. Right? So you try 18, actually 18, right? So this
okay.
You try 1, that's too much. Okay. Yeah, you try different lambda and you see how the test data, because how it performs on the test data talks, right? Or you say the validation data, right? You never see. Okay, so they are still different.
It's observable.
Yeah, so then you will use a validation data to try to overcome this. Okay, so this is what we will see next. Let's see whether we still have time. So this is called the model choice. Okay, so here's what we have so far. Let me see. Yeah, I try to avoid using the. I think Zoom's annotation is not compatible. Okay, so here is what we are here so far, right? So you know that the lawing lambda should go from 0 to negative infinity, right? When your lambda is go from 1 to 0. Okay, right. And then you use another data. Usually we call validation data. Okay, to test. Okay, and when you train, of course, you will see the error increase. Okay, so I mean the error is the first part, the root mean square. Okay, so if you look at the error, we're talking about the first part, this part. We're not counting this part. Okay. When we do the validation, parameter choosing of the lambda. We only look at the first part. Okay? Right, because the second part is the artifact to avoid overfitting. Okay, the first part will always increase, right? Because you are trying to tune to this guy, right? So, but we are not trying to tune this guy. So when you have another optimization target that is more favorable, you add this lambda weight. Of course, this error will gradually go bigger because it try to optimize the right-hand side, the second part more. Okay, so your training error will always increase. Okay, but your test error will decrease initially, right? Because it's generalized better because of the introduction of the regularization factor, right? The second term, okay? But gradually, if you go too much, it will increase, right? For example, if you go too much, flatten everything, then these errors go back to big, okay? Right, initially it goes to, basically it's go from this kind of shape, then it becomes smoother, 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 and then maybe it becomes this shape. And then you further increase lambda, it becomes this shape, and error increase again, okay? So this is where you will choose the value. It should be somewhere here, right? And again, if you have multiple choice, you choose the one that makes things the simplest. Okay, you will probably choose this one. Okay, that's a small lambda. Any questions? Yeah, so let's continue. Right, so here are the examples. So you can see that this negative infinity means lambda is equal to 0, right? If lambda is 0, this lambda, long lambda goes to negative. This means, hey, we don't have any regularization, right? Because the second term, the weight is 0, right? Then we get very big values. If we're 18, these values now look more reasonable, right? So because their square is in the loss, okay? You don't want to get those values. And if we go too much, right? So then we, of course, we flatten everything to 0 because it's null, right? So you want to minimize the vector length, okay? So you want to find a good spots in between, right? So this is basically, yeah, so the concept of overfitting, right? And regularization. Any questions? So basically, we have several stages, right? So the first stage is called end fitting, right? If you don't have enough data. Hello? I think Mse should mute yourself, okay? If not, I need to mute all. Okay, so yeah, so yeah, let's continue. Yeah, finally, we will have an introduction to supervised learning first. We will go to the other problem later. Okay, of course, we are not going to deep reinforced learning and deep learning. Okay, and so we will potentially cover some of the deep learning stuff. Okay, like try more advanced models because we want you guys to have hands-on, even if for those models you have never learned, you are still able to use it, right? So otherwise, you have to know how to build a television in order to watch it. That's unreasonable. Okay, but we need to teach those fundamentals. Okay, so you have a good mindset about machine. Right. So yeah, so task. Okay, so the first task is about the classification. Okay, we want to learn a task from examples, right? Let's look at the classification example. Here we have a positive examples which are family cars. And we want to differentiate family cars from other cars, right? Maybe sports cars, etc., or the very crappy cars, right? Not safe for a family, okay? And so the training examples are labeled by human, right? So that could be human error, by the way, okay? So, and we want to do is class learning, right? If we see a car's attributes, right? And we immediately know whether it's a family car or not, okay? So this is what we try to do. And the input feature, right? So we always talk about what's x1, x2, x3, and then we have y. Okay, y is obviously a class, right? Whether family car or not. Okay, and we use positive to mean family car, negative to mean other car. Okay, and the input feature x1, x2, x3, right? So what are they, right? So here in this example, we consider only two features. One is the price, right? So the price, if it's very low, maybe it's a crappy car, very unsafe, right? So a couple of thousands, right? So maybe. And then if it's super expensive, maybe 100K, maybe it's a luxury car, right? So in the middle, maybe it's a family car, okay, right? So another engine power, right? So if you have very crappy engine power, then maybe it's a crappy car, right? If your engine power is too strong, maybe it's a sports car, right? So So yeah, in the middle, it's more like a family car. You don't want to drive super fast, right? So it's risky, okay? And if you have a family, of course, the engine cannot be too low, right? So the power should be high, okay? So let's look at this. So this is to give you some intuition of this scenario, okay? Now, the training data is always like this. We have X, which are vectors, right? So, and we have Y, okay? Vector means X1, X2, X3, these are the attributes, right? Here we only have price and engine power, okay? And Y is family car or not. Okay? So we can plot them here, right? So here, X, this is, let's say, engine power for this point, and no, this is the price for this point, and engine power for this point, right? So this is two-dimensional, okay? And for each point, we have its price and engine power plotted here, okay? And then the Y, right? So when we talk about the Y, that the target to predict, it's actually some dimension come out of the screen, okay? Right? So this, these are the optimized, the variables to input, right? So you want to predict the other dimension that are coming out of your screen, okay? So this is the right way to view it. Now we are using, you know, once you have examples, you can always use different labels to mean different cars, right? Some people like to use 1 to mean positive, 0 to mean negative. In some scenarios, it's more convenient to make it a -1. Okay, so this is because, you know, if it's a -1, then it's kind of 0 is in the middle ground, right? So this is negative, this is positive. This is useful in other scenarios like support vector machine, we'll see later. In more like a neural network, or it's the traditional way, it doesn't matter. Right? 0 is the first class, maybe negative or background. 1 is the first another class, right? Maybe 2 or 3. Okay, we can use this notation. So there are some practice of doing this. Okay, we'll see that later. All right, so let me take a look at the time. We don't want to go by. Oh, so it's already only 3 minutes left. Let's see whether we can finish this quickly. Okay. So one example is this, right? So remember, we use P1, P2 to mean if we assume our model is a box, okay, as a rectangle. The rectangle can be defined by the lower left corner and upper right corner, right? Lower left corner is the price 1 and engine 1, okay? Engine power 1. Price 2 and engine power 2, right? If it's in the middle ground of both range, then we think it's a family car. Outside, it's probably a sports car, right? This could be a luxury car. This is a crappy car. Okay, right, so this is assuming that we have a rectangle, right? So just like our polynomial function, right? So we can assume it's like a ellipse, for example, then oval, right? So then it's another kind of model, okay? So, but then we have the model parameter we want to train, right? So whether it's this rectangle or this rectangle, okay? So for this, this model itself is a hypothesis, okay? So basically, we will have different kind of rectangles that can differentiate them. And in the next class, we will continue here. Okay, that's all for today. If you have any questions, I will be online for 2 more minutes. Otherwise, that will be all for today's class. Do go through the lecture note and also the slide. Okay, so they are helpful. Okay. And I think the TAs should already send an announcement of their office hours. Okay, if you have not seen them, you feel free to send email to me and also to the TAs. Okay, so that's all for today. Thank you, everyone. And I think next week is Labor Day, right? So potentially it's a holiday. So I will see you maybe in 2 weeks, right? I will double check, by the way. Right. Okay, thank you, guys. And if you have any questions, just let me know. Right. Yeah.
Assignment.
Hello?
Yes, the assignment that you have, the Python assignment, that is not.
I actually don't remember. I don't think.
Yeah, I don't have assignment right now, but we will release an assignment potentially in the middle of this week. Okay, and that will be about image annotation. So you know, you need to give why, right? So and giving annotate data is.
Don't worry, you can just ask help from them and he helps you. And use case, making a use cases shouldn't be that difficult. You can.
The demo that you sent, I think there's an assignment in the Python. I think in the Python notebook that you attached.
Okay.
Are you talking to me?
That's fine. That's fine. You can just refer your own assignments that you have done or someone else's assignments, or you can just ask your friends for old assignments and refer those. Even those are really helpful.
Pratash, I think you are broadcasting. Okay.
Oh, sorry, my bad.
Yeah, I thought you were asking me. Yeah. And if you have any questions, I will be still online for maybe 1 minute. Okay, if you don't stop me, I will just get offline.
Hi, Professor. What about attendance?
Okay, can you repeat? Sorry, I didn't get it.
Sir, what about attendance, sir?
What are the what? Sorry.
Attendance.
Assignments, right?
Attendance.
Attendance.
I'm asking about attendance. Yeah.
Oh, yeah. So, yeah, I didn't take attendance today, right? So,
okay.
Yeah, I will take attendance next class. Yeah, so I will run the sample. Yeah.
Yeah. Thank you, sir.
You're welcome. Yeah, if you have no questions, I will get offline. And remember, we have two 2-hour slots for Q&A with the TAs, right? And we'll also upload the video for you guys to look at. Right? So, and also, so you can also send email to me if, let's say, the TAs are not answering your question properly and you can still not understand it. Right? So, and we may have the assignment in the middle of this week. Okay, we'll release it, and the assignment will be in 2 weeks. So no worry. Okay, yeah, and yeah, if you don't have any questions, I will just get off. Okay. Thank you.
All right. Thank you.
About the group project. Are you going to form the group, or do we have to form our own group?
Oh, you need to form your own group. Okay, so, and if you cannot find a group, you can do it individually. That's also fine. Okay, and the group size should be at most 4. Okay, otherwise, if you have 20 students working on a simple project, that's a trouble, right? So, yeah, and we will give more information on how to form groups later. Okay, we will do that in Canvas. Right?
Okay.
Okay, so then I will get offline. If you have any question, just send me email. Thank you.